Welcome back. So last time we introduced the concept of U-substitution for doing indefinite integrals, that is, for doing antiderivatives. This time, let's continue on and do some more complicated examples and get a feeling for how to do U-substitution for various problems. Let's start by reminding ourselves of what the basic rule looks like. So the setup for U-substitution looks like this. We are trying to compute an indefinite integral of f of u of x, u prime of x dx. So what the U-substitution rule says is if you have an integral that looks like this, then I can do it by rewriting it as the integral of f of u du. In other words, you can do this integral as if you're just doing it with a new variable called u. And the kind of mnemonic for remembering how this works is to think about this thing as representing the quantity du. So in other words, du should be should represent u prime of x dx. Okay, to make this more concrete, let's just work out some examples of this. So let's do a simple one first right away. How about the indefinite integral e to the sine x cosine x dx. Okay, so the idea is we'd like to look at this and say that we have some function, the exponential function, something else stuck inside of it. This is our u of x function, the sine x in this case, and then multiplied by the derivative of that guy with a dx in front. So to apply the U-substitution rule, what I would do is I would set u to be the sine of x. I would say that du is the derivative of this with a dx in front. So du, the derivative of sine is cosine x with a dx in front. And using this, the rule says that I can rewrite this integral as an integral in u, namely e to the u du. Like magic, the sine and the cosine have disappeared. We're left with this really easy integral just with the exponential function. And exponential is its own derivative, so like we're done. That's e to the u plus c. We're kind of done because we'd like our answer to be in terms of x. So we have to say that u is sine x plus c, and that's our final answer. Okay, so that's the basic idea and how it's applied in a simple context. Let's just do now a few more examples so that we get a little bit more practice with this idea. As I've mentioned, integration is more of an art than a science. And so really, what we have to do is get a feeling for how to apply these rules in various contexts, really just by experience and examples. So let's take a look at this one. We're going to use U-substitution to do this. And so the question is, what should we call u? And let me just tell you what we'll try for u first. We're going to do on this one, we'll let u be the sine of x. Okay, what does that buy us? So if we let u be the sine of x, what would du be? Du, by our conception or formula of what du is supposed to mean, is the derivative of this guy, the cosine, and then with a dx in front. So if I look at this expression that I have up here, I can interpret this as my u, my du. This is actually just u du. Okay? I mean, we could have thought of this as, I have this thing stuck inside of some function and then its derivative next to it, but what's the function I'm sticking it inside of? It's kind of the function f of x is x. It's the du is the itself function, right? The idea. All right, okay, so u du. So now I'm going to actually integrate this very easy integral. You get 1/2 u squared plus c by the anti-power rule. And then we complete the problem by substituting in for u is the sine. And we're done. Okay, good. Now we have a feeling for it. And of course you see that the issue is always, what should we make u? And this is really a trial and error thing, but which gets better with experience. Okay, let's try another one. Let's integrate the tangent. This is great. It doesn't look like anything we would use U-substitution on or anything else. But if you take a look at this and think about what the tangent is in terms of sine and cosine, sine x over cosine x, then we can read this as we have something next to the dx. So we're going to want sine x dx to be our u. Right? So I'm thinking about this as 1 over the cosine x, sine x dx. Okay? So we want this thing to be our du at the end of the day. So what am I going to do? Let's start by trying u is the cosine of x. Okay? So if u is the cosine of x, then du would be, well, the derivative of the cosine is minus sine, actually, so we'd have a minus sign there, minus sine of x dx. Okay, well, I can do that. Let me just put an extra minus sign here, right? I mean, I can make the, I can put a minus sign in the bottom and a minus sign on the top. Now I have a minus sine x dx. That's this whole thing is my du. So I can write this as, so I have 1 over negative u, and then the rest is my du. So all that stuff is my du. Or really I have a minus 1 over u du. The integral of 1 over u is the logarithm. So I get minus the ln of the absolute value of u du. What is u? U is the cosine, so I get minus the logarithm of the absolute value of the cosine of x. Excuse me, I don't have a du there. I just integrated it already. That's a plus c. The ln of the absolute value of the cosine plus c. That's a perfectly valid answer. Just for some reason, in a lot of calculus books, you'll find that this answer is also written by using the logarithm rules, which says that if you have a minus sign, this is like minus 1 times that, and that can go in the exponent there. So I can write this actually as the ln of 1 over the absolute value of the cosine. Or in other words, that's the logarithm of the absolute value of the secant, because that's what 1 over the cosine is. All of these are valid answers. They're all the same thing. And that is the integral of the tangent. All right, so practice makes perfect. We're still going to do a few more examples. There are still lots of interesting shapes of integrals to do. You get better and better the more you see and the more you practice. So make sure you try some yourself and not just watch me do it. But let's see a few more examples. I'm really excited about this next integral. I can feel the geometry all around me. All right, so for this integral, as usual, the question is going to be what we should make u. So again, we're looking for some chunk to call u, and we're looking for then something like its derivative sitting next to dx, right? So the pattern is we're looking at f of stuff, and then stuff prime times dx. So this where stuff is what we'll call u, and this part is what we'll call du. Okay. And so in this thing, we want some stuff multiplied by the dx that's going to be our u prime, right? And so this is a reasonable candidate. So is this the derivative of some part of this expression? It's like the derivative of x cubed, kind of, right? So you might, at first, try to make u just x cubed. But what you'll find is that if you do that, the problem still stays relatively complicated. It gets easier, though, if instead of letting u be x cubed, you let it be 1 minus x cubed. The point being, the derivative is almost the same, but this whole expression here is just a u now, and that makes our life easy. Okay, so if we let u be this, we'll let du be negative 3x squared dx. In other words, we take the derivative of u, it's the usual procedure, put a dx in front, then what we see is that this is just a square root of u, like it should be, like we'd like it to be. But the du, we don't quite have this du, we're off by a factor of minus 3. Okay? There's a lot of different ways that people try to sort this out. Let's just do one of them here. One way to sort this out is to, basically multiply and divide by minus 3, right? So I can rewrite this as, well, this is the part that I kind of like, that I understand, that I know how to deal with. It's really, the u is right there. But the part that I want now is I want to have a minus 3 x squared dx. So to stick that minus 3 there, though, I should actually have to divide by a minus 3 also. So maybe I'll have a 1, oh, sorry, I already had a 1 up there. I'll have to stick a minus 3 in the bottom so that the whole thing I haven't changed. Right. So if you rewrite it like that, then I can actually pull out that minus a third and write this as 1 over the square root of u, and this whole thing is du. Okay, so now we can finish this off with our good old anti-power rule, writing this as u to the minus 1/2 du, and the rule says, there's a minus sign there, excuse me, and the rule says that I just add 1 to this whole thing, so this is adding 1 to a half, where I get 1 over 1 minus a half, it's minus a half plus 1, that is to say, u to the, 1 minus a half. It's kind of awkward to look at psychologically. Let me write this as minus a half plus 1. That's what it is. 1 more than that thing. The minus a half plus 1 plus c. And just let me write this as normal people might write it. So this is a half. This is really 1 minus a half is a half. And you flip that over and that's a 2. And this is a half. Plus c, or in other words, to finish this all off, I have 2/3. U is 1 minus x cubed to the 1/2 plus c. Of course, I can write that as a square root, but whatever, that's a valid answer, and we're done with that one. Okay, let's just do one more of these problems. This last one, we're actually going to do 2 U substitutions. We're going to do it, and then we're going to do it again. So just so that we don't confuse ourselves, we're going to change the name of the variable, of course. So we'll do U substitution, and we'll have a V or something like that. Okay, so let's do that, and then we'll be the masters of U substitution. All right, so here's the problem that we're going to do. We're going to take the antiderivative, or the indefinite integral, of x secant squared of x squared, tangent of x squared dx. Now, you could actually do this in one step if you're clever, but we're just going to pretend we're not very clever today, and we're going to just try to do this in a logical, kind of plotting step-by-step way to try to make it as clear as possible. So we're going to look at this expression and think, how can we make it at least a little bit simpler? Because what we can see is that there is at least kind of what's next to the dx, right? I mean, you can either, one thing, we have this, we wrote it over here, but x is kind of multiplied by the dx, right? The order of multiplication doesn't matter. And this x is close to the derivative of x squared. So the point is, we can simplify our lives. We can make this a little bit easier to look at by making the following U substitution, by letting u be x squared. If we let u be x squared, then the du is going to be the derivative of x squared, 2x times dx. Now, so I need a 2 instead of just my x. So I'll do that. I'll stick a 2 in there and then pull it back out. How about I'll rewrite this as the indefinite integral of 1/2 secant squared of x squared tangent of x squared. I didn't write my x, I'm going to write it over here, but I'm going to stick a 2 in front. So this 2 and this 1/2 net worth is 0, right? I didn't do anything, or 1, it didn't do anything, multiplied by 1. And so but I have a 2x dx, so I just wrote my x on the right instead of the left. This thing over here is my du. And so what I can do is I can rewrite this as 1/2 secant squared of, now x squared, the whole point was that this x squared I can now just write as a u, okay? So secant squared of u, tangent of u, du. This is a bit easier to look at, right? I mean, I'm not done, but I've, helped myself out a bit. Okay, now, so to finish this off, what I'm looking for is another U substitution. I want to look at this expression, and I want to say that I have something maybe stuck inside something else, but I have one piece, and I have another piece that looks like it's derivative. Well, of course, we know the derivative of tangent is secant squared. You see a tangent, you see a secant squared, you want to think one is the derivative of the other. That's just the way we are after doing calculus, right? So we say this is, so a natural thing to do would be to say, we'll let v be the tangent of u. Let's just formally say that v is the tangent of u, and then what would dv be? You take the derivative of tangent, which would be the secant squared of u, du. Okay? So now if we look at this expression, then you can now rewrite this in terms of the u's and the v's. So this is 1/2 the indefinite integral. If I write this a little bit backward, this is my v, and this whole thing is my dv, right? dv is secant squared u du. So this gives me a 1/2 v dv. Wow, now we're talking about an easy integral. This is just 1/2 of, how do I take an antiderivative of v to the 1? It's 1 over 1 plus 1, which is 2, v squared plus c. The answer is 1/4 v squared plus c. But what is v? v is the tangent, right, of u. So this is 1/4 the tan squared of u plus c. But what is u? u is x squared. So this is 1/4 the tan squared of x squared plus c. And boom, we are done.